2 on practice exam 4 of chapter 1 in the book Problem Solving with Differential and Integral Calculus. We have an experiment here. We have 500 grams of water in a beaker at 5 degrees Celsius at time equals 0. We put it in a room. Temperature is constant 20 degrees Celsius, and we monitor the temperature of the water. The water is going to warm up because it's in a warm room. So part A asks, what's a good estimate of the initial rate of the temperature change? Right here at the origin, time equals 0. How quickly is the water heating up? Part B asks for the rate of change of temperature at 4 minutes, right here. Part C asks for the temperature of the water at 1 second. A very small time after it started to heat up. Let's start with part A. To get the rate of change of temperature, the rise is the temperature change, the run is the time change. The rate of change of temperature is temperature per time. And that's the slope. So there's a good tangent line. We have to get the slope of that tangent line. It goes from 5 degrees to 20 degrees. We're going to use this triangle right here. We have to get the run. The run's going to be a little bit hard, a little challenging. Let's draw a vertical line to see where it crosses the horizontal axis. So that's 0.4, 0.8, 1.2, 1.6, a little bit bigger than 1.6. It's an estimate. I called it 1.64. The rise is 15 degrees. The run, 1.64 minutes. The heating rate is plus 9.15 degrees Celsius every minute at the beginning of the experiment. The heating rate goes down as the water warms up. Part B, what's the rate of change of temperature at 4 minutes? So let's identify that point. There's a dot right here. Let's draw a good, careful tangent line. There it is. We have to get the rise over the run. We can use any triangle we want. Let's use one that makes it easy. It hits the axis here at about 16, goes up to 20. That's 4 degrees Celsius for the rise. The run, we have to get all the way over to here where it crosses 20 degrees. So again, draw a vertical line, 4.4, 4.8, 5.2, 5.6, a little bit less than 5.6. It's an estimate. Again, I called it 5.56 minutes. So the rise goes from 16 to 20. The run goes from 0 to about 5.56 minutes. The heating rate is 0.72 degrees Celsius every minute at 4 minutes. It's different at different times because it's changing. The temperature change is nonlinear. Part C asks for the temperature at 1 second. Right down here. These are minutes, so 0 minutes, 2 minutes. 1 second is way in here. There's the dot. I identified the point. What's the temperature here? It's hard to read off the graph. It's a little bit bigger than 5. But we know what the rate of change is. It's 9.15 degrees every minute. And the slope of this line, the slope of the tangent line at 0 is virtually the same as it is at 1 second. That slope of the line is not that much different. So we can just use the slope of the line. The slope is the rise over the run, and we know what the run is. It's 1 second. We have the slope, we have the run, we can calculate the rise. It's a simple, direct proportion. The slope is 9.15 degrees Celsius every minute, which is 9.15 degrees Celsius in 60 seconds. And if we're close to 0 and we can use 9.15 degrees Celsius per minute, which we can at 1 second, we can calculate delta T by just multiplying both sides of the equation by 1 second. So delta T in 1 second is 0.15 degrees Celsius. That's the change in temperature. It started at 5. So at 1 second, it's about 5.15 degrees Celsius. That's problem 2.